All right, so I've been plugging your book, man. I've been while you haven't been here, but I just wanted to ask you how you doing. How's your life been doing right now? You okay? Everything going good?
Things are okay. I just came back from Phoenix, and yeah, things are okay. I'm excited about the book,
Yeah.
um, and which is somewhere there. It is. You can't.
So May 9th, book
May
release.
9th. That's right.
Yep, it's pre-orderable on Amazon, correct?
Yeah, yeah, and hardcover and Kindle and audiobook, so you can choose
Excellent.
your and or do all three.
Yes, please. And of course, all of the other Lawrence Krauss excellent books like Universe from
Thank you.
Nothing, The Physics of Star Trek. I mean, we could. Oh
Thanks.
yes, I'm so excited to have you here. I wanted to ask this. This is the first thing I have to ask. How do the Heisenberg compensators work?
Very well, thank you.
Yes,
That's what Michael Okuda said
you
when I
got it.
asked him that. Okay. Yeah. Anyway, it's the
Yeah,
only
that was
answer
my
as far as I
favorite.
can tell.
I mean, just before we get into the book, is that even something even worth thinking about teleportation?
Well, it depends. If you're a quantum system, then teleportation is a good thing to imagine. But we're not very good quantum systems. If we were, we could sort of go through walls and things like that.
Yeah.
So, um, so you have to have a very specially prepared quantum mechanical state to be able to teleport the information from one, place to another. And
Mhm.
you can do that with electrons or photons if they're very carefully prepared, but not with you and me. So it ain't gonna happen.
No. Okay. Yeah. The too much. Uh, is it indeterminacy?
Well, what happens is that complex systems like large objects, the quantum mechanical correlations, which allow this spooky action at a distance, which is the sort of
Mm.
basis of quantum mechanics, which I do talk about a lot in the new book,
Oh,
um,
yes. We're about to get into that.
because I think it's important to talk about quantum mechanics. Those things get washed out when lots of particles are interacting, and once those correlations are gone, then systems behave classically like we're used to with like baseballs and cannonballs.
Yeah. So it no longer becomes just this realm of like near infinite probabilities, right? It becomes
Yeah.
much more
Well, it becomes
realizable.
classical. It becomes the world we're
Comes
all
in
used to.
classical. Exactly.
Yeah.
So let's talk about the edge of knowledge. I know that the first chapter of your book is time. Is that right?
Yeah, yeah. The five sections are time, space, matter, life, and consciousness, which are probably
Oh,
the key fundamental questions that people ask
perfect.
about the world.
Perfect.
And I can't resist taking it down from here, even though it's up.
Take it down. Show it to
Yeah,
us.
yeah, yeah. There, this one. I just got it yesterday, as you know, because I tweeted it. Anyway, so I hadn't seen the actual physical thing.
I like the cover.
Yeah, me too. There
Yeah,
was a vote, but I liked it anyway. But it was just what people voted on among two
I love it.
choices. Anyway, yeah. So time is the first sort of, because it's probably the most immediate and in some ways the most mysterious aspect. We still really don't understand time, but and as I talked about, some people wonder whether time's an illusion. But I say that doesn't mean that whole question I can't quite see the importance of, especially if you missed your train to work. I think time really isn't an illusion.
Hmm.
But the fact that time in the context of general relativity behaves differently in different systems in the presence of gravity. And of course, one of the things I talk a lot about is what happens near a black hole. And
Hmm.
we still don't really, well, of course, we don't know the ultimate nature of what happens at the final point of a black hole collapse. But we do know something really weird, which is that when you go enter into the event horizon of a black hole, then sort of time becomes space-like and space becomes time-like. So that time has a finite future because you're going to end in the singularity, but space actually inside the black hole, because you can move around in different directions, and when you're looking down, you're seeing things that fell in the black hole before you. When you're looking up, you see things
Yeah.
that are fell in after you, and so space, in some sense, becomes infinitely big because space becomes time-like in the sense that looking that 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 when you're looking in one direction, you're really looking in the future, and when you're looking in the other direction, you're really looking at the past. And and that
Hmm.
switch of space and time is very weird, but it's just a property of the fact that um, in different gravitational circumstances and different coordinate systems, namely when you're falling inside of a black hole, what you call time and what someone else calls space can flip.
Yeah.
It's really weird.
So the modern consensus right now is that space time is fundamental, but people like Donald Hoffman are saying that space time is not fundamental, that it emerges.
Well, look, we don't know, and that's the whole point of the book. We know a lot, but there's a lot we don't know, and it's okay to not know things. And so the
Yeah.
question of whether space and time are emergent or not is something a lot of people have thought about in the context of quantum gravity, but we didn't. Uh, uh, we don't. We have no idea, and these are questions that remain to be answered, and we really need a fundamental theory of space and time and quantum mechanics to understand them. And the whole point is that right now we have no theory that clearly describes our universe in which where quantum mechanics is merged with space-time. String theory is a possibility, but generally the universes that it describes don't look like the universe that we live in, at least. And so we're not at all certain of these fundamental questions of whether space and time are emergent, and
Yeah.
indeed whether we assume that quantum mechanics is fundamental and we need a theory of gravity that is consistent with quantum mechanics. But some very good physicists have argued that maybe quantum mechanics gives way at very small distances. I'm betting that's not the case, but some really,
Yeah, I would like
Gerhard
to hear.
who won the Nobel Prize keeps arguing that. And so, but right now, unfortunately, it's all speculation because we don't have a theory of quantum gravity, and it's one of those things that we know we don't know. It's the limit where, on such small scales, when gravity becomes a strong enough force to not be ignored. Because what people don't realize is that although gravity appears to dominate our lives every day when we try and climb up the stairs, gravity is the weakest force in nature,
Yeah.
and and for almost all intents and purposes, gravity is ignorable, except it turns out on very, very, very small scales. Then gravity becomes sufficiently strong that you have to worry about what are called quantum corrections of gravity, and then all bets are off because we know general relativity right now is not consistent with a quantum theory.
Can't be reconciled. I see what you mean. Let's talk more about what's the next chapter.
Okay, well, the next chapter, as you might imagine, after time, is space. And
Space.
there are
Okay.
lots of open. I mean, as I describe it, well, I think someone reviewed it and said this. What I try and do at the beginning of each chapter is list sort of the outstanding questions that we don't know. We don't know. And does space have an end? Is there a smallest distance? Are there extra hidden dimensions? What's the geometry or shape of space, if you want? And is
Mm-hmm.
space fundamental or emergent? Just like the question of time. And these are all questions I try and bring people up to the forefront by explaining what we do know and we don't know, and of course the interesting thing about space is really the fact that our picture of what we mean by a universe has changed tremendously. When I was younger, when I was just beginning in the field, a universe meant everything. All right, almost by definition, it was everything.
Yeah.
But now we have a much better definition of what I think the universe is, an operational one in the sense of Einstein, that our universe is that region of space with which we could have communicated in the past, could have communicated to us, and with which we can one day communicate in the future, even if the future is infinite.
Right.
And that's much more reasonable because if there's regions where we can never have communicated with and we'll never communicate in the future, then they're really essentially separate universes. And
Yeah.
because if you can't communicate with them, there can't be any causal impact. One cannot affect the other. And so what we kind of realize now is it's most likely, and it could be quite likely, that there are essentially an infinite number of universes or a large number. I just completed a podcast which will appear sometime in the next few months, I guess, with my friend Andre Linde, who helped develop a theory called inflation. And one of the things about internal inflation is that basically universes keep getting born amidst this ever-expanding, faster and faster background space. And in each such universe, the laws of physics could be different. And that idea of a multiverse in which a lot of separate universes exist that have different laws of physics is really quite it's a new one, and for some people very disappointing, because when I was becoming a physicist, one of the things I wanted to do was learn why the universe is exactly the way it is and why it has to be.
Yes.
And now it turns out that physics may be an environmental science, that our universe the way our properties of the universe may just be accidental, and they are what they are because if they were different, then we wouldn't be here to ask the question.
The
And,
anthropic principle, yeah, that kind of
well,
thing.
yeah, and it's got, and people misunderstand it and misuse it a lot. And it's not something. It's not really a principle, but it's a possibility, whether we like it or not, that if there are many universes, that the explanation of the fundamental constants of nature may not be anything more than well, they take many values
Yeah.
and it's an accident. And that's may seem depressing, but as I say, the universe isn't what, or let me put it this way, the multiverse isn't what it is to make us happy.
I know in my mind when I look at an atom, it's like a field of potentiality around it where an electron can form, right? But how does gravity fit into any of that? How can I make my brain understand gravity at those levels?
So it took Einstein a long time to do that.
Yeah.
But the basic idea is that Einstein realized came out of what he called the Gedanken experiment, a thought experiment, and that is that, and it was the experiment of that's similar to what many of us have done in our lives, but we didn't follow it up like Einstein did. If you're in an elevator and you accelerate upwards, you find yourself being pushed down to the ground, right? And he pointed out that really, if you're in empty space and an elevator is accelerating upwards, and you did every experiment you could do, and you let things go, they accelerate down towards the ground at a uniform acceleration, which is exactly what we see on Earth. So an accelerating elevator is indistinguishable from being at rest in a gravitational field. Okay?
Yeah. Yeah.
But then he said, well, if you shine a light ray through one hole of the accelerating elevator, the elevator's going up, you shine one light through one hole, the elevator's accelerating. So if it goes in halfway up the elevator, by the time it hits the other side, it's going to be closer to the bottom. If you're in the elevator, it looks like the light ray curves downward. Now, light travels in straight lines in space, so the fact that the light ray is curving might mean that space is curving, basically. And so he said, ultimately, what he recognized is what we call a gravitational field is equivalent to the fact that the space in which we're living is curved. And we can think of gravity as being completely equivalent to the curvature of space. And that's what essentially Einstein's equations tell you, is how space curves in the presence of matter.
Yeah.
Newton tells us in the presence of matter there's an attractive force between objects, and Einstein tells us in the presence of matter or energy, space curves, and that curvature of
So
space
it's like
determines how things move. And so that's the relationship between gravity and space-time, in the sense that gravity reflects the curvature of space-time.
Okay, that makes complete sense.
And a flat space is equivalent to a space with no gravity. And
Okay.
and so that connection then leads to a whole, well, not only a theory, but a whole bunch of phenomena that would not exist otherwise. And it makes general relativity more complicated because of that nonlinear sort of feedback. Because matter and energy determine the curvature of space, but the curvature of space determines the motion of the particles within the space, and that feedback
Yes.
makes general relativity a much more complicated theory, but much more interesting at the same time.
Yeah.
And there were a variety of predictions, and one of which, of course, was that light would bend in a gravitational field. And it turns out light would bend twice as much as you'd imagine in the case of Newton. And that's what, luckily for Einstein, when he first calculated it in 1914 or so, was he predicted that the effect would be half as big. And they were going to measure it by looking at an eclipse, but the First World War happened, and they had to delay until the end of the First World War. And by that time, he'd corrected his prediction.
Yeah.
And so when they actually measured in 1918, when Sir Arthur Stanley Eddington and a team went down to South America and actually could see the fact that distant star in an eclipse, of course, you can't see stars behind the sun or near the sun when the sun is shining, but in an eclipse you could, and the stars were in a different place than they should be, indicating the light had bent around, and by the amount that was exactly predicted by Einstein. And that's how he became famous instantaneously, almost. His name was on the front page of the paper. He wasn't famous at all. People don't realize for E equals MC squared or any of that stuff, his special theory. He's well known among the physics community, but he became a worldwide celebrity over the fact that he had a new theory of gravity and it worked.
Yeah.
And of course, every prediction of general relativity that we made um, has been verified, including the fact that time changes in the presence of a gravitational field. That clocks,
Yeah.
if I hold a
Time
clock up
dilation.
here, it takes a different rate than if I hold it down there, and that's
Yeah.
amazing. And as I talk about it, and in fact, I first wrote about it maybe 15 years ago. I don't know, in an article I think I wrote in the Los Angeles Times. I can't remember. That if we didn't take that effect into account, then the GPS on my phone wouldn't work.
Right.
Because
Yeah.
the clocks on the satellites, which the light ray is bouncing off of in order to, or the microwaves or the electromagnetic waves are bouncing off of in order to be able to see distance. Those clocks are ticking at a different rate than the clocks on the ground. If we didn't take that into effect, within a few hours, our GPS detectors would be off by kilometers. So we depend upon that very subtle aspect at the frontier of physics. We depend on that every day to get to the grocery store or wherever we're trying to get with our GPS.
Yeah. It's quantum tunneling that it has to do, right?
Well, there's no quantum. That's not related to quantum tunneling. That's just related to a very simple fact that
maybe I was thinking about something.
There are 3 satellites, right? And they have atomic clocks on them. And basically, by having a light ray bounce off where you are and come back, you can measure the time it takes. And if you have three satellites, you can triangulate, knowing that light travels at the speed of light, and find out exactly where you are. That's why you usually need 3 satellites for a GPS to work. But it only works because the atomic clocks are completely synchronized and be able to measure time to a millionth of a second or so, because of course it doesn't take light long to travel back and forth. But nevertheless, because they're up above the Earth's surface about 10,000 miles or so, they're in a different gravitational field, and their clocks are ticking at a different rate. They're also moving very fast, and special relativity tells us that the clocks are actually slowed down because because they're moving fast. But it turns out general relativity tells us that they're actually ticking faster than clocks here on Earth. That overwhelms the special relativity effect, and it turns out, I think, those clocks are changing by something like 38 microseconds a day. I think I once calculated. I forget, something like that. Which may not seem like a lot, but when you're trying to measure distances to meters, it takes a billionth of a second for light to travel a meter. So if you're off by microseconds, then you're off by thousands of meters. And so we have. That's why we have to depend on that very subtle effect that gravity affects time, and it's pretty interesting.
No, that's awesome. I thank you for explaining that to me, because I didn't know that's how satellites worked. And is that time dilation?
Time dilation. That's right.
Okay, so that happened to like 2 Soviet astronauts where they aged. In fact, do you remember that?
Well, yeah. I mean, the astronauts have aged probably a millionth of a second less than we have.
Yeah.
I don't think it's going to.
And then, of course, people who fly, closer to the.
Well, I mean, when you're going in a plane, you're traveling faster than the person on the ground, and it was first measured. This effect was first measured by taking a 747, more or less, and traveling around the world and coming back and finding that the atomic clock on the plane was not exactly synchronized with the one on the ground. But the effect is microscopic because we're traveling so slow compared to the speed of light. The effects of both special and general relativity depend upon your relative motion compared to the speed of light. And so we're talking millionths of a second here. We're not talking about anything significant, which is one of the reasons why it was never recognized. I mean, that's a key fact, right? All of this was true, but it was hidden because the effects are so small on our scale. Now, when we look out at the universe, where we're looking at places where gravity is incredibly strong, like black holes near the center of galaxies, we're seeing these effects become significant, but because they're immense gravitational fields. But that's something that's relatively new, and on Earth, if we weren't doing things like GPS and other things, the effects of general relativity could be ignored, which is one of the reasons why it's so subtle and amazing that Einstein first discovered them.
That's crazy that it was that subtle and he found them. I mean,
he was thinking, and he was extending his ideas of special relativity. And again, he was motivated in some sense by observations. There was an observation that Mercury, which goes around the sun, All the planets are ellipses. And if Newton's laws are true, then the ellipses should be perfect. The planets should just stay in the same orbit. But in general relativity, there are corrections, so the ellipse precesses over time. And no one knew why the orbit of Mercury was precessing by still a very small amount, in absolute terms. And when Einstein developed his theory and he calculated the precession of what's called the precession of the perihelion of Mercury, and got the right answer, he said he had heart palpitations. That's the first time he almost fainted, because then he realized his theory was right. So space and time are connected by general relativity, and these questions are interesting ones. And a part of what I've been doing as a living as a scientist is worrying about cosmology, is asking the question how what is our universe infinite? How could we tell? And what are the constraints? And then the third chapter, the third section is about matter, which is our understanding of the fundamental structure of matter, and quantum mechanics, of course. And there's a lot of books written about quantum mechanics that make it kind of seem, I like to think they're trying to make themselves seem smarter by talking about the many worlds interpretation.
Oh yeah,
and I think a lot of that is just self-serving on the part of the authors, because as I talk about, my late colleague and friend and one of the brightest physicists at Harvard when I was there was a guy named Sidney Coleman. And as he pointed out, talking about the interpretation of quantum mechanics is getting it asked backwards, because the world is fundamentally quantum mechanics. So you can't expect to explain it in terms of this classical illusion that you and I have. If anything, we should be talking about the interpretation of classical mechanics. So anytime you impose some classical picture on quantum mechanics, you're going to get something that looks really weird. But you shouldn't think that weirdness is fundamental. It's just because you're describing it in terms of an approximate theory, and a lot of that weirdness is just because we're not thinking about it correctly. And so I tried to reproduce this beautiful lecture that Sidney gave called "Quantum Mechanics in Your Face." I first heard it probably at Harvard, and so we can try to understand some of the properties of the weird world of quantum mechanics, and it is a weird world that's incredibly. Again, my phone wouldn't work if it weren't for quantum mechanics. Quantum mechanics is at the heart of everything we use now in our society, and so it's weird, but it works, and as far as we can tell, there's no doubt that there's no evidence that it's not completely fundamental. And then space, time, and matter are the three fundamental sort of physical questions about the universe, physical issues that I try and talk about what we know and what we don't know, what the open questions are. And both in particle physics, the fundamental aspects of what are the fundamental forces of nature.
Yeah. Is
quantum mechanics fundamental? And then I segue to life and consciousness, because I think for most people the big fundamental questions are, how did life originate, and is there life elsewhere in the universe? And those are big questions.
Those are.
And I talk about those, and we made a lot of progress in there, and a lot of non-intuitive things about how life might form. And then the last section of the book is, for me, the area where I think we know the least, which is consciousness. I've spent a lot of time talking to people on this. Obviously, it's not my own area, but again, it's interesting to see that in both life and consciousness, a lot of the people early on who started to investigate this were actually physicists, which is kind of interesting. And still, some people, like Roger Penrose, think that quantum mechanics has something to do with consciousness, quantum gravity. I don't think so.
Yeah, his orchestrated objective reduction.
And I don't buy any of that. But I think the point about consciousness is what makes it so difficult to try and get a picture of it is that we're stuck in our own brains. We don't get to. And when we look from the outside, when I'm talking to you, I'm not experiencing your consciousness. I'm experiencing, and I can ask you questions about why you do things that you do. But as I talk about, people have done well-known experiments to show that the rationale that people give for why they do what they do can be completely wrong. And there are great experiments about people who for one reason or another, the connection between the two hemispheres of the brain has been cut. Used to do it for epilepsy. And they'll give arguments for why, that turns out, the right side motion of the right side of your body is sort of, its motion is covered by the left side of your brain, left or right. So when you feel when you feel something with your hands here, it's this part of the brain here. But if I block you out, so you can only see one
Right.
part of the what's going on, and
Yeah.
the other side of the hemisphere happens to have to do with language, the
Yeah.
other hemisphere, and so you'll give arguments for why you do things with your hands that are actually totally not the case, but because your brain is trying to rationalize things. So and I think, and so I talk about what the challenge of even defining what consciousness is. Just as defining what life is, I point out, is not so easy. If you try and think about, um, uh, if you ask what defines life, let me ask you what defines life. I'll put you on the spot.
Well, I read it the other week. It was like the biological need for food and all that kind of stuff. But I would say life in general could be like silicate life. You could have all kinds of.
No, but what are the properties that define a living thing versus a non-living thing?
Hmm.
You see, it's not so easy.
No, it's not
You
easy.
might say, well, it reproduces, it has
Yeah.
metabolism.
Hmm.
And then I would argue, as I argue in the beginning of that chapter, that if that's the case, then fire is alive, right?
That's right.
Fire
Yeah, that would be
reproduces.
true.
So you've got to be a lot more careful in what you think about when you talk about the distinction between alive and not alive. Well, as difficult as that distinction is, it's much harder to say what consciousness is.
Yeah.
It's hard to,
Way
and in
harder.
fact, a lot of people who study consciousness hesitate to even define it.
Yeah.
We can, and the point is, we can even isolate how certain things in the brain work, but that's not the same as understanding the phenomenon, the emergent phenomena of consciousness that we all
Yeah.
seem to experience, and that we all have this imaginary, being in our head that is us, that is I.
Yeah.
And so a
The
lot of
self.
people say that that the self is an illusion, like some people say time is an illusion. I also find that kind of a useless argument because we all experience a sense of self. So
We do have a self. Yeah.
the world that we experience is an illusion in the sense that quantum mechanics is fundamental and we're experiencing this class world. But saying it's illusion doesn't help you at all. The question is, how does that illusion arise? And I end with the fact that the late great physicist Richard Feynman
Oh man. Yeah.
once said that if you can't build it, you don't understand it. So I think
right.
I think ultimately if we're ever going to understand consciousness, it may arise if we can ever build artificial systems that are
AI.
conscious.
Yeah. Yeah. I
And
think that's
and,
yeah.
and then I talk about the fact that that a lot of people are scared of that, and there's recently been a big petition, which I actually sort of signed only because I thought ChatGPT is a little too woke, and we should take a little time to think about that. But I'm not as afraid of artificial intelligence as some people like my friend Elon Musk. I think the world is going to be different, but
Yeah.
it's going to be, but that doesn't mean it's going to be a lot worse. It's
No,
going
I
to be
talked
different.
to Roman. Do you know Roman Yampolsky?
Well, I don't know him, but yeah.
We works with Elon. I talked to him, and he's an AI specialist, and he says, he's very worried. And then I'm kind of like you, man. I'm like I'm not worried. I think we'll probably find out more answers about what experience and consciousness might be.
Well, as I like to say, I'd like to find out what an artificial intelligence thought about physics. What questions of, and in fact, that's by the way why Feynman first proposed quantum computers. Actually, he was the first person to talk about it because he said, well, maybe if a quantum computer is using quantum mechanics in its calculations, then it will kind of understand quantum mechanical questions that we can't understand. And so maybe it'll help me understand quantum mechanics. And it's in fact, probably the first use of quantum computers right now, the simple ones we have, is to perform quantum mechanical calculations that are simply too complicated for classical systems to perform. But a quantum mechanical computer quantum mechanics involves all of these correlations and many, so many more interrelated intermediate stages of a calculation that it quickly becomes so complicated, even for a system of 4 or 5 particles, that it would take longer than the age of the universe to be able to do that calculation. But if a quantum system is doing it, it's doing all those calculations using quantum mechanics, parallel processing, if you wish, at the same time. And so quantum computers can help us understand, say, chemical bonds and that
Yes.
sort of thing. But
genetics,
Plato
right?
thought
Like
maybe it would help
genet.
understand quantum mechanics. So anyway,
No, you're good. You're good. It can help us understand like genetic algorithms, right?
well, maybe. I mean,
Yeah.
and there, the question is whether practical large scale quantum computers will be buildable. And I used to be much more skeptical than I am now. I think it's going to take time, but I think like many things, there's a lot of hype right now. But I think it's quite likely that we'll have quantum computers that can do um, that can reveal a lot, and to what extent they ultimately will be able to um, uh,
To do for us, yeah.
succeed. Will
Yeah.
will time will tell. But there's a lot of smart people working on it.
Yeah, and what's the one? The IBM has one the size of a car, right? And they've got it cooled down
Well, it's
to.
the size. I think that the number that's called qubits. Basically, it's
Yeah.
this. Here's the difference. You see, my iPhone has maybe 5 billion separate little
Mm,
um, memory cores in it, if you want to think of it that way.
mhm.
And the largest quantum computer right now has uh, I think 58, something like that, 58 quantum memory cores. So we're talking about, so it's not, even though it's large, the number of quantum memory cores that can be kept coherent, if you want to call that, and for any
Okay.
length of time is a very small number. Now, if you could keep 58 of them going and for a length of time, you could still do remarkable calculations that you couldn't do with my little iPhone with its 5 billion memory cores, but or bits. Uh, but that's the challenge, I think.
You explained all of that like perfully. I
Well, that's
love
good. It's the
listening.
first time I've
So
talked
thank you.
about my book, really. And in fact, it is the
Thank you.
first time I've talked about my book.
Well,
I
Travis,
mean, it doesn't appear for a
Travis
month,
told me
but
about it.
I should say I'm
Yeah.
hoping that people will. Obviously I write things so people read it, but I am also hoping people will get the book because right now I think I'm going to be doing some events in England happily, but I expect in
Yeah.
North America that there won't be any reviews or interviews and by mainstream media of the book, and so the only way to get the message out is by word of mouth and if people buy it in advance, maybe more bookstores will carry it. It's kind of an unfortunate thing, but
That's
but
very
but
sad.
anyway, it is what it is. So
Mm.
I'm hoping that we can buy that we can encourage people to read it to read it because I think it's worth reading, obviously. But
I
and
think it's worth
that way
reading.
maybe that way because it's people don't realize independent bookstores are independent, but they depend. They follow the crowd, and if things
Yeah.
are reviewed and by mainstream media, then they'll carry to the bookstores, but they won't otherwise. And that's I'm quite sensitive, I should say, to that. I mean, I talk about it being on Amazon. It is, but I'm quite aware that many people would rather buy things from their local bookstore than buy from Amazon. And
Yeah.
I've always enjoyed independent bookstores, but you have to realize that in order to go to your independent bookstore and buy it, they have to know that it's there, and so
Yeah.
and it's
How can we
self-serving. It
best?
sounds self-serving to say that, and it is self-serving,
Well,
except it's also true.
how can we best help the situation? Because I want people to care about physics. You know what I mean? I know the
Well,
math.
I think that the whole point of I'm going to be writing an op-ed, but the epilogue of this book is about the importance of being willing to say I don't know, and
Yes.
I argue that important aspect that science is all about. We get excited by not knowing, but in our society right now, both on the left and the right, part of the problem of this dogmatic ideology that's interfering with universities on the one hand and government on the other is people who have this absolute certainty in that they know everything, and that it used to be religious, right? It used to be a religious dogmatism that I used to fight, but now it's a kind of secular dogmatism, and I think that we really that the world could be a better place if people say, I don't know. Maybe I should listen to the other person and maybe learn something. Um, and and so that's why I think this kind of thing is useful beyond just the fascinating questions it deals with, but the moral that comes with it. And I end by saying it's very true that it was when I read books by people like Feynman that I first realized there was something left to do. And I think I'll read you the last paragraph of the book if you want.
Please do. Oh, that would be
I said, as I remarked at the beginning of this book, focusing on the edge of knowledge has provided me an opportunity to explain how far we've come, but it also allows me to present some guideposts for the future. When I was a teenager, I remember reading a book by Richard Feynman called The Character of Physical Law. I had always been interested in science, but that book made it clear to me for the first time that the really interesting questions in physics had not all been answered yet. It was an invitation to me, and it presented a challenge and an opportunity to try to move on to the next step. I don't presume that this book will have the same impact on some young person today, but I hope it does. Indeed, that's why I've written it. So,
that's
anyway.
beautiful. Excellent. I mean, that's what I care about, is educating kids about this kind of stuff. I want physics to be in the minds of high school students. You know what I mean? Like, I want that to happen.
I think the world, I mean, I hope so, because these questions are so fascinating. And I've often said, when it comes to teaching, more teachers, as well as more parents, should be willing to say, I don't know. Because that's an invitation to discovery. The question, it should be, I don't know, but let's learn together to see what we do know. Instead of regurgitating some old facts, it's, hey, I don't know, let's make it a voyage of discovery for both of us.
Yeah.
And I think it's only teachers who are good and feel confident and comfortable are prepared to say, I don't know. The ones who are not are too insecure to acknowledge the fact that they don't know. And that's a shame.
That is a shame. And that's what we do here, me and Travis and all of us. We are okay with I don't know. We want to sit with it. We want to stew in it. And we want to, like, search through the internet and through real life as many different ways as we can, like, get closer to the truth. You know what I mean? At least that's what us physicalists here like to do. So,
well, it's, I think it's nice to have a conversation, and that's one of the reasons why I came on here. And I'm gonna be doing an event with Travis on my own foundation. My own foundation, the Origins Project Foundation, which tries to, connect people to the world of science and connect science and culture. I think we'll sponsor it. So I know we're going to do an event in Vancouver, which I'm excited about in October.
Okay, well, we've got so many callers lining the book out. Who do we want first? Scott, you want to go ahead first?
Yeah, I just wondered, have you ever thought about having, like, Dean Kamen in with some of these discussions? Him as a engineer, I find him to be, like, somebody who is actually really pushing scientific literacy very, very thoroughly.
Well, I'm in favor of trying to have people who build things, and I know Dean Kamen is, and that's certainly something I consider. I think the whole point of what I try and have on the podcast are a wide variety of people who are all leading us into the future. And that includes not just scientists, but artists and filmmakers, as well as engineers. And I think it's important to have that balance. I mean, we theorists often tend to get the limelight because all this stuff sounds so fancy, but the people who build things are actually doing it. And I admire them tremendously, a lot more than I did when I was younger. I didn't really appreciate it. Now I kind of look back and realize how in some sense, how much I miss by not being someone who builds things. But I certainly try and have people who are making things that work. And Dean came. And I've actually asked Elon to be on, but he doesn't even have to smoke. He doesn't even have to smoke marijuana to come on.
Well, you have to if you come here. I swear it. You must if you come here.
Okay.
No,
I'll remember that.
No, remember that. Yeah, write that one down. Honenheim, go ahead and ask your question, buddy.
Hi, Lawrence. This is an absolute honor. I won't spend too long kissing your ass.
Oh, no worries. Thank you.
You in the world makes it a better place. I'll be very quick. So it seems more
probable than not. I appreciate that.
Thank you. Oh, it's so cool to talk to you.
I agree with that. Yeah.
So it seems more probable. Oh, that's so cool. So it seems more probable than not that there's no free will. And I've been sharing that video of yourself and Richard Dawkins when you were asked by an audience member. So it seems we're subject to the laws of physics, and as a result, our neurological states and the external world. Therefore, would you be in support of drastic changes to our society, most importantly, education and crime and punishment, so a more formative education and retributive justice system was made?
Well, look, there's a lot of things to parse in that question, but I think it's clear that on a fundamental level, there is no free will. You know, my favorite answer to that was given by my late friend Christopher Hitchens. You know his answer when he asked him if he believed in free. If he believed in there was no free will, he said, "I have no choice." But nevertheless, the world is a complicated place. So it's true that ultimately there's no free will, but the world is so complex that for all intents and purposes, we live in a world that acts like there is free will. So people still need to take responsibility for their actions in some sense. There are, even without going to the atomic level, there are reasons people do things, and of course, a lot of those reasons may involve a childhood trauma or other. So we should certainly be more when it comes to crime and punishment. We should be much more understanding and sympathetic, and the purpose of separating criminals from people who aren't should not necessarily be to punish them so much as to try and obviously rehabilitate. That's not what we do in our prisons. But I think we cannot, even though there's no free will, we cannot absolve ourselves of the responsibility for what we do, because, as I say, it's in the world at a human scale with so many complex interactions, so many reasons why we do what we do. Effectively, it's indistinguishable from a world in which there is free will. So we have to be able to, we can't just absolve ourselves and say, I had no choice. What I did was not based on choice. It was based on choice, but your choice, of course, is influenced by many other factors. And when you go down to some atomic level, it may all be involved with a second order differential equation called the Schrodinger equation, which is deterministic. So I do think we have to recognize that we have to be more sympathetic and less into punishment and more into rehabilitation. But I absolutely think that we cannot say that a world with no free will means that no one is responsible for their actions. I don't think that logically works. That's my argument.
Thank you so much. I disagree a bit, but I won't take more time. I'd love to have a conversation.
Well,
sometime.
Well, I mean, it's an issue that one can certainly discuss and disagree with, but I would love to be able to find anything that distinguished a world in which there was free will from the world in which we actually live. And I can't see any, as a scientist, as a physicist who likes to think if you can't measure it, then it's hard to define it. That I know of no experiment that can distinguish at our scale, at the scale of you and me, where we make decisions, a world in which there was free will from one in which there isn't. And because of that, I think we have to effectively act like we have free will, and understanding the underlying reasons, and that should impact in some sense upon how we behave as a society. But it doesn't absolve us from personal responsibility, in my opinion.
Yeah. Thanks, Honan.
Thank you.
Great.
Thank you so much.
Sure.
Have a wonderful day.
Thanks. It's been a pleasure. Thank you.
We've got Peter here. Peter's one of our friends from the Travis Pangburn Hangout.
How you doing? Can you hear me?
What's up, Peter? Yes,
I can hear you.
Okay. I was going to ask, how has the work of Hawking been put to bed with regards to grand unification theory? Or has any progress been made on the subject?
Well, so another long question with a lot of things to parse there. But Stephen's work was involved in trying to understand the fundamental nature of space and time, and the fundamental trying to understand quantum effects. He became famous for what's called Hawking radiation, which is the first example of how quantum mechanics impacts on gravity in a way that's strange. But grand unification is a theory of particle physics where we try and understand the fundamental forces, and eventually we hope to incorporate gravity in it. That's what string theory tries to do. But on all scales larger than an incredibly microscopic scale, because the Planck scale, gravity is irrelevant. And when it comes to grand unification, we can ignore gravity. We try to understand how the forces we understand, the strong, weak, and electromagnetic forces, may be unified at some incredibly small scale, which which while it's incredibly small, is nevertheless could be much, much larger than the scale where quantum gravity becomes important. And maybe they're the same scale, we don't know. But,
Has it been
but when we
dropped in
try and
general?
understand, the way to try and understand that is generally, although one of the things I've done my whole career is to try and use the universe as an experiment, because the early universe had energies far beyond that, where we can probe at particle accelerators now. But nevertheless, we try to build particle accelerators that explore the fundamental nature of matter on the smallest scales that we can directly explore here on Earth, and we look for clues that'll lead us to that to a possible understanding of unification of those fundamental forces. We had hoped the Large Hadron Collider would tell us more than it has. It already discovered the fundamental feature that unifies two of those forces, electromagnetism and the weak force. We'd hoped it would find something else that would lead us in a new direction. It hasn't done that yet, and it might not. But, we're trying that, and at the same time trying to look at remnants, signals from the beginning of time when we look at the large-scale structure of the universe. We're trying to use everything in our toolbox to try and tell us what the right picture is, and we don't know. And that's, again, one of the things we know we don't know. And we know that, but what we do know is if we stop asking those questions and stop doing experiments, we're not going to get the answers, because we're not going to get it by pure revelation, by sitting around, staring at our navels in the middle of the night. We are guided. Science is empirical, and physics is an empirical discipline like the rest of science. And the only way we'll move forward is by experimental results, because nature's imagination is far greater than the imagination of human beings. And we need to be guided by nature, and that's why we need to look at, build telescopes and look out, and build accelerators and look within. And you might say, well, why? What the heck? We don't, we got problems here on Earth, and we do have problems here on Earth.
No,
But
this stuff is super important.
The amount of money that's spent, or that needs to be spent to ask those questions, is minuscule compared to the amount of money we're wasting on weapons, for example.
I so agree with that.
Thank you very much.
The defense budget is probably $600 to $800 billion a year, and the budget of the National Science Foundation to cover all of science is maybe $8 billion. And so, and the cost of a big accelerator might be $10 billion, but that's spent over 20 years. And so, on the scale of if it was a matter of feeding people or doing physics, that'd be a different question. But it's not. It's not.
Yeah. One last question, Perry, and then we got to let him go.
Alrighty. Thank you, by the way.
Sure. Well, thank you.
No, thank you. Unfortunately...
no, thank you.
Unfortunately, here in America, we abide by the nature of capitalism, so I do hope that your book does reach those larger crowds of consumers.
Well, we'll see. Me too.
Yesterday, like Thomas said, we talked a little bit about space and time. We're philosophers here, not physicists. So the question more or less was, is time mind dependent or mind independent? I know you mentioned that it may be an illusion, but maybe not really. Perhaps if
I don't think it depends on consciousness. Although, you know what, when Einstein was asked to explain relativity, I talked about it in the early part of my book. He said, okay, if you're sitting on a hot stove, a second can seem like an hour, but if you're talking to an attractive person, an hour can seem like a second. That's relativity. And it's certainly true that our sense of time is, an hour can go by like that if we're having fun. So our conscious perception of time certainly depends on our consciousness, but the ticking of clocks doesn't depend on consciousness.
No, exactly.
There's far too much emphasis put on consciousness. Consciousness is a emergent state that comes from a complex system that's our brain, but it doesn't govern the way the world works. It's not. There's this illusion about consciousness and quantum mechanics that somehow, if we didn't look at the world, it wouldn't exist, and that's just nonsense. You don't need conscious systems to involve measurement and to impact on the way the quantum mechanical systems evolve. So, while our perception of time is very personal, the physical aspect of time is completely independent of our consciousness.
Gotcha. I appreciate that. Thank you.
Sure.
Excellent. Lawrence, I love you. I love you, man. I love talking to you and hearing you talk.
Thank you, and thanks to everyone for being patient with me. And I'm sorry I came in late, but it was a pleasure.
Thank you.
We love you very much, man, and for everything that you've done, and thank you for influencing me and everything that I've done.
Okay.
So thank you.
Okay, you all take care and have a good evening.
Have a good one. Bye, bud.
Take care. Bye-bye. Bye.